Okay, our next two videos here are going to be in-class problems that we worked through. So they weren't specifically sample problems, but what they were doing was looking at mechanisms that had rate-limiting reactions. And we talked about slow initial steps, which are going to be kind of the easy one to think about, and then second, we'll do fast initial steps. So just as a concept to remember, when we talked about slow initial steps, and we had our little demonstration here with paper stapling and taking apart, when we had the slow initial step, we said that stapling was going to happen once every 10 seconds, or the rate constant was 0.1 per second, which means that we only really had one happening every 10 seconds. So whoever was doing the stapling could staple them together, and then they'd have to wait till a count of 10 before they could staple another one. Our fast reaction was somebody ripping those two stapled papers apart. And they had a much faster rate constant, tenfold faster. So they could do their chemistry, taking apart those papers, one every second. So they had to take them apart, count to one, then they could take another part. So conceptually, what we could see with this is that our overall chemistry was limited by the first step. That reaction had to count to 10 before it could be repeated again. If we see that the two papers being together is an intermediate, we never saw the accumulation of intermediates because as soon as this guy was made, it was immediately used by our fast step. Rate law for these reactions are always going to be the rate law for the slowest step. So that's what we're going to work through with this in-class problem to kind of validate that. So again, looking at what we have here, looking at this reaction, if we were to assume that this was an elementary step, right? Elementary step means that we can write a rate law using coefficients as exponents or reaction orders for our rate law. So if we were to write this, assuming it were an elementary step, we'd write rate equals rate constant times the concentration of NO2 times the concentration of CO. Okay, that's how we would write if this was a one-step reaction, so it was an elementary step. The rate law would look like this. Well, in sample problem 3, we actually used the method of initial rates and we used experimental data to actually derive the rate law, so the actual rate law. And the actual rate law is rate equals the concentration of NO2 squared. So in this problem, we showed that the reaction is second order with respect to NO2. It's zero order with respect to CO. And remember what it means for something being zero order. Zero order does not mean that that species is not important for the reaction or you don't need it. It just means that the rate is not dependent on its concentration. So we can't change the concentration of carbon monoxide here and affect the rate of the reaction. However, the rate of the reaction is in a second order sense dependent on the concentration of NO2. But what's really important to note here is these do not match. Okay, our experimentally determined rate law does not match what we would propose if this was a single step or an elementary reaction, which means our reaction takes place through a two-step mechanism. Now, I would never expect you to derive what these steps are, but what we have through the rest of this problem here is a proposed mechanism. We're proposing that a first step is two NO2 molecules reacting to make NO3 plus NO, and then an NO3 molecule reacting with carbon monoxide to give us NO2 and CO2. For this mechanism, we're proposing that the initial step is slow and the second step is fast. So, again, what we need to do here, if we want to validate a mechanism, right? Criteria for validating a mechanism, we have to make sure that the elementary steps sum to the overall balanced equation. So let's kind of take a look at what we have here. We're going to see that we've got an NO2 over here and two of them over there, so one of them can cancel. The NO3 is going to cancel, and the NO3 again is one of those species that we'd refer to as an intermediate. And once we sum this up, we're going to have NO2 plus CO gives us NO plus CO2. And that's what we have as our given equation. So we know that that matches. So our elementary reactions that we're proposing balance sum to the overall balance equation. In addition, our elementary steps are reasonable. This elementary reaction is bimolecular, as is our second reaction. So those elementary steps are reasonable. Now the last thing that we need to do is figure out if the mechanism that we're proposing correlates with the experimentally observed, the actual rate law. So what we need to do for that is we need to figure out what the rate laws for each elementary step are. Okay, so jumping back up here, we can write rate laws for each elementary step as rate equals rate constant times the concentration of each species raised to powers that are coefficients. So for our first step, the rate law equals the rate constant times the concentration of NO2 squared. For our second step, the rate equals the rate constant times the concentration of NO3, again to the first power, times the concentration of CO. Now, importantly, the rate law for what we're proposing to be the slow step must match the observed rate law. Okay, that's what we say here. The rate law for the rate determining step must match or becomes identical to the observed rate law. Okay, so what we can see here is that this mechanism is valid. We're proposing that the first step is slow. The first step has a rate law that matches that of the actual rate law. Okay, so our three steps that we'd have to propose cross off for our mechanism to be valid, we can cross off, so that works. Kind of another couple of things just to point out with this mechanism. Again, because the first step is slow, we do not accumulate this intermediate. As soon as any is generated, it's used up, just like we saw with our stapled papers in our little in-class demonstration. We never accumulated the stapled papers because as soon as they were made once every 10 seconds by our slow stapler, once every second they were torn apart by our next person. Again, just to point out, carbon monoxide does not appear in the rate law. It's zero order. And the reason is it appears after the rate determining step. The only species that appear in the rate law are those species that are part of the slow elementary step. Okay, this might be one of those videos that you might want to think about and then watch again to kind of listen to again, because thinking about reaction mechanisms when we talk about slow and fast steps can get kind of complicated.